Hello students, welcome to the next class which deals with regular and normal spaces. Okay, first we will see the definition. What's a normal space? So first we will discuss what is a regular space. So regularity is a property of a space which is defined at a point. Okay, so suppose we have a topological space X2 and we take a point small x belongs to capital X. We say that this topological space X2 is regular at X. X is regular at X if we consider any closed set C in X which does not contain Y. We take a point X, we say that X is said to be regular at X if we consider any closed set C, which is a closed set, okay. Any closed set C not containing X. Then this definition says that there exist disjoint open sets U and V such that X in U, C is contained in V. There exists disjoint open set U such that X belongs to U and open set V such that C contained in V. And U and V are disjoint, they have no common elements. So which is the property of regularity at a point X? The whole space X is said to be regular if it is regular at each of its points. If it is true for any point X in capital X, we say that the space is regular. Okay, so which is the basic definition of regularity in topological space? So I repeat, if X is a point and C is a closed set, it must be closed, okay. C is a closed set not containing X, then there will exist disjoint open sets U and V such that X in U, C in V. Okay, right. Now we will define what is a normal space. The normality of topological space says that when a space X2 is normal, suppose we have a topological space X2, it is normal means you consider two closed sets C and D. Two closed sets C and D, okay. C and D both are closed sets. Then if C and D are any two closed sets, then there exist two disjoint open sets U and V. There exist two disjoint open sets U and V such that C contained in U and D contained in V. Remember, U and V are disjoint. U and V are disjoint and C and D are any two disjoint closed set. For every two actually disjoint closed sets, every two disjoint, if X is said to be normal, if for every two closed disjoint sets C and D of X, there exists disjoint open sets U and V such that C contained in U, D contained in V. Remember, C and D are disjoint, U and V are disjoint. If C and D are disjoint closed sets, then there will exist two disjoint open sets U and V are open, okay. U and V are open. So this is the definition of normal spaces. Ready? Then we will see some examples. Before stating the examples, I will define one more definition. What are T3 spaces? We already discussed the separation axioms T0, T1 and T2. Now we will define what is a T3 separation axioms. T3 axiom. T3 axiom. T3 axiom says that X is a T3 space. A topological X2 is a T3 space if it is regular and T1. When a space is both regular and T1, then that is called a T3. So a space is said to satisfy T3 axiom if it satisfies the T1 axiom and it is a regular space. Okay, this is called it. What is T3? T3 equal to, I can say, T1 plus regularity. Okay, then one more definition. I can define T4 axiom. What is a T4 axiom? A space, topological space X2 is T4 space if it is normal and T1. So I can say T4 is nothing but T1 plus normality. So T1 plus regular implies T3, T1 plus normal implies T4. So T3 and T4 axiom similarly defined. Okay. So we have defined so far. There are five separation axioms: T0, T1, T2, T3, T4. T3 and T4. Okay. For example, consider indiscrete topological space. Indiscrete topological space. So X together with the topology tau I, indiscrete topology. Okay. So we see that, we discussed that this indiscrete topological space can't satisfy the separation axioms T1, T0 and T2. Okay. Now we will check, is it satisfies T3 or T4. Since it cannot be T1, it can't be T3 or T4. Because when T3 means it must be T1 and regular. Even though it is regular, we can't say it is T3 because it is not T1. We know it is not T1, right? And since it is not T1, it can't be T4. Clearly, since it is not T1, it is not T3 or T4, right? But we will check the regularity and normality. What will happen to these two properties for this space? Okay. So to see the regularity, I'd consider, let X belongs to capital X and C be a closed set, right? Closed set in X such that X not in C. So C be a closed set not containing the point X. Okay. Right. Since X belongs to capital X and C be a closed set in X such that X not in C, you know, in the indiscrete topological space, the closed sets, the only closed sets are in the space, the only closed sets are empty set and whole set itself. Then if you consider C as a closed set which not containing the point X, means C must be empty. So empty set is a closed set not containing the point small x. Okay. Then we want disjoint open set to contain this point X and the closed set C, right? So I take U equal to the whole space X and V equal to empty set. Then clearly the entire set and empty sets are always open in the any topology. So in this topology, X and empty set are open, implies U and V are open. And clearly what is U intersection V? X intersection empty, it is empty. So U and V are disjoint. Disjoint open sets. Now since clearly X belongs to capital X implies X belongs to U, right? And C is equal to empty means empty set will be contained in empty, that means C is contained in V. V is empty, C is empty. So you get there is two disjoint open sets U and V such that X belongs to U and C is contained in V, right? Which implies indiscrete topology is regular. Regular at X, since X is arbitrary, it will be regular at each of its points, therefore it is regular. Yeah. So even though it is not a T3 space, it is regular. Okay, what happened to the normality? For proving the normality or to check the normality, I have to consider by the definition. What is the definition of normal sets? Normal topological space. Normal means if you consider two disjoint closed sets C and D, there will exist two disjoint open sets U and V, such that C in U, D in V. Okay, so to check that, to check normality, I consider let C and D be two disjoint closed sets in indiscrete topology. Yeah. Since in this topology the only closed sets are empty sets and X, when you have to choose the two disjoint open sets C and D are equal to either empty and X. or vice versa. Yeah, so suppose C equal to empty and D equal to X. This is the only choice for C and D. Okay, then take U equal to empty and V equal to capital X, right? Then U and V are open, because empty sets and entire set will be always open. So U and V are open, disjoint also, disjoint sets in capital X, such that C will be clearly contained in U because C and U are empty. Okay, and D will be clearly contained in V since X and D and V are X, right? So which implies, if you consider in discrete topology, if you consider two closed sets C and D that are nothing but one is empty set, one the whole set, then you take U as the empty set and V as the capital X, then that will be the corresponding disjoint open sets to contain disjoint closed sets. So indiscrete topology is normal. So even though it is not T4, it is normal. So indiscrete topological space is an example for normal space and regular space, but not T3 and T4. Right? So in this example, or by this example, I can say that T4 space always implies regularity because it is regular plus regular plus T1, right? So T4 ആണെങ്കിൽ ഉറപ്പായിട്ടും അത് regular ആയിരിക്കും. But regularity doesn't implies T4 because the T1 must be true for that spaces. Yeah, there is a missing term which is T1. T1 കൂടി ഉണ്ടെങ്കിലേ T4 ആവുള്ളൂ. So in order to get this T4, we must want T1 axiom. So indiscrete topological space is an example which is not T1 but it is regular and it is not T4. So it is regular but not T4. But not T3. I'm sorry, T3 space. T3 space doesn't imply regularity and regularity doesn't imply T3. T3 space always implies regularity. I'm sorry, there is a mistake. Not T4. In this case, it is T3. Regularity doesn't imply T3. മനസ്സിലാവുണ്ടോ? And this is an example is also true for T4 implies T4. What is T4? Normal plus T1, right? When a space is T4, that will be surely normal. So T4 axiom always implies the property normality. But normal space need not imply T4. Normal plus T1 will imply T4. Okay. So normality doesn't imply or need not be implies T4. So which is also an example. What? Indiscrete topology. So indiscrete topology is normal but not T4. And indiscrete topology is regular but not T3. So this indiscrete topology does not satisfy any of the separation axiom T0, T1, T2, T3 and T4, but it is regular and normal. Okay. Now we will see one more example. Our strongest topology, discrete topology. So you consider the discrete topological space. Discrete topological space. TOD denote discrete topology. Okay. Yeah, we proved that it is T2 and it is T1 and it is T0, right? You know, this X with TOD is T2, T1 and T0. Yeah. What happened to T3 and T4? Is it regular and is it normal? So let X belongs to capital X and C be a closed set in X such that X not in C. So we consider a point and a closed set not containing that point. Now to prove the regularity, we want two disjoint open sets U and V such that X in U, C in V. Right? Yeah. Then you take U equal to singleton set X. Then discrete topology, in discrete topology every set will be closed and every set will be open, right? So singleton set X will be closed and singleton X will be open. So I consider singleton set X as an open set. Okay, then U is an open set in X. Okay, Since the indiscrete topology is also has a property that every set is closed, singleton X is a closed set also. Then you consider X minus singleton X. You take V equal to X minus singleton X. Yeah. Which is then V is open. Then V is open in X. Why V is open? Since singleton X is also closed in discrete topology. Okay. Closed with respect to discrete topology. Therefore, X minus singleton X endavum open out. X minus singleton X will be open in discrete topology. Yeah. So you consider X minus singleton X as V, then V is open in X. Okay. So U and V are open. What about U intersection V? Singleton X intersection X minus singleton X. It's clearly empty. ഒരു സെറ്റും അതിൻ്റെ കോംപ്ലിമെൻറ്റും ആണ്. A set intersection, its complement is always empty. Yeah. So U and V are disjoint, which implies U and V are disjoint open sets in X. Okay. Now we will prove X belongs to U and C is contained in V. Clearly X belongs to U because U equal to singleton X. Yeah. What about C? C is a closed set not containing the point X, right? And V equal to X minus singleton X. Then clearly, since X not in C implies C will be contained in X minus singleton X. So that is C will be contained in V. Okay. So which implies if you consider any point and a closed set C, there exists disjoint open sets U and V such that X in U and C in V, which implies the discrete topology is regular. And you know it is also T2, T1 and T0. We proved that. So which implies discrete topology is regular and T1, which implies discrete topology is, when it is regular and T1, it is T3. Now we will prove the normality of discrete topological space. How will you prove the normality? To prove the normality, I consider to prove the normality we want two disjoint closed set and two disjoint open sets containing that, right? So let C and D be two disjoint closed sets in X to D. So you consider C and D be two disjoint closed sets, right? Then we want two disjoint open sets to containing C and D separately. Yeah. How will you choose U and V? You take U equal to X minus D. Okay. Since D is closed, its complement X minus D will be open, right? X minus D is open in X. So U is open. D itself. Since it is a discrete topology, D is a closed set, implies it is an open set too, right? Since it is discrete topology, every set will be open and closed. All are open sets. So D will be open also, right? Discrete topology, D is also open. So if we choose V equal to D, then V is open. Okay. And what about U intersection V? U intersection V equal to X minus D intersection D, which is always empty. So U and V are disjoint open sets. Now we need only prove that C is contained in U and D is contained in V. Okay. Clearly D is contained in V because D equal to V. And what about C? C is contained. Can you say that C is contained in X minus D? Right. Yes. Because we have, I will write here, because we have C and D are disjoint closed set. So C intersection D is equal to empty. When C intersection D equal to empty, C will be contained in X minus D. and x minus d is chosen as u. So which implies c will be contained in u. Okay, so c is contained in u. Since d equal to v, d is clearly contained in d implies d is contained in v. So you get for disjoint closed sets c and d, there exists disjoint open sets u and v such that c contained in u and d contained in v, which implies discrete topology satisfies normality, and it is also T1, right? So which implies x with 2d is both normal and T1. So which implies discrete topology is T4. So discrete topology satisfies all the separation axioms. Therefore discrete topology satisfies all the separation axioms. All the separation axioms T0, T1, T2, T3 and T4. And note that indiscrete topological space does not satisfy any of these separation axioms even though it is normal and T1.